Welcome to the new physics project, initiated by Joseph George. Our current understanding of the universe is built upon the foundational frameworks of special relativity, general relativity, and quantum mechanics. However, this project introduces a bold new perspective, that space is permeated by a form of matter continuously generated from mass defects occurring throughout the cosmos. Microscopic analysis of spent nuclear fuel offers both experimental and empirical support for this idea, revealing signs of rapid volumetric expansion, where missing mass appears to transform into a previously unrecognized state of matter. This discovery challenges the fundamental assumptions of relativity and quantum theory, offering alternative explanations for the very phenomena they seek to describe. Welcome to the new physics.
Microscopic analysis of spent nuclear fuel as evidence for the EXP. Microscopic analysis of spent nuclear fuel as evidence for the explosive mass defect hypothesis. The explosive mass defect hypothesis posits that the mass lost during a nuclear reaction, commonly referred to as the mass defect, does not merely convert into kinetic energy, but rather undergoes an explosive transformation into a new form of superthin, space-filling matter. This theory departs from conventional interpretations, where the energy released in fission is predominantly attributed to the kinetic motion of fragments and prompt emissions. One of the most compelling pathways to test this hypothesis is through the microscopic analysis of spent nuclear fuel. What is spent nuclear fuel? Spent nuclear fuel, SNF, consists of the residual nuclear material left in a reactor after it has undergone fission reactions over a period of operation. It contains fission products, actinides, and residual uranium or plutonium. Conventionally, SNF is analyzed for its isotopic composition and radiation characteristics. However, under the explosive mass defect framework, microscopic structural examination of SNF provides a new empirical lens. Hypothesis: microexplosions leave microscopic structural traces. According to the hypothesis, each nuclear fission event involves a microscopic explosion, driven by the instantaneous and localized conversion of the full mass defect into a burst of energy that produces shock waves, pressure fronts, and rapid structural transformations. These events are hypothesized to produce spherical or radial damage zones, voids, nanocraters, and shock-induced deformations in the surrounding nuclear material. Such features would differ qualitatively and quantitatively from damage expected from mere fragment recoil, neutron irradiation, or thermal stress. Microscopic analysis techniques. Several modern techniques are used to probe the microstructure of SNF. Scanning electron microscopy, SEM, allows visualization of surface topology, revealing crater-like formations or spherical indentations. Transmission electron microscopy, TEM, offers nanometer-scale imaging of internal lattice disruptions, dislocation loops, and amorphous regions. Atomic force microscopy, AFM, can detect ultrafine topographic variations. X-ray diffraction, XRD, assesses strain patterns and phase transformations within the fuel matrix. Electron backscatter diffraction, EBSD, maps grain boundary damage and crystallographic changes post-fission. If the explosive mass defect hypothesis is valid, one would expect to find radial patterns of damage, shockwave-like dislocation distributions, and non-thermal, non-ballistic voids that align with the expected characteristics of microexplosive detonation. Empirical indicators and observations. Preliminary observations in certain high-resolution SNF studies, not previously interpreted in this framework, show nanovoids and bubble formations around fission tracks, localized grain pulverization inconsistent with standard heat gradients, radial symmetry in microfracture zones, suggestive of shockwave origin rather than linear momentum transfer. Evidences of recrystallization or melting in zones too small to be explained by typical thermal conductivity paths. These features, while documented, have often been attributed to generic fission damage or thermal cycling. The explosive mass defect hypothesis provides an alternative and unifying explanation for these otherwise anomalous patterns. Implications for physics and engineering. If validated, the hypothesis would profoundly affect our understanding of energy transformation mechanisms in nuclear physics, the nature of mass-energy equivalence, suggesting that mass loss produces not only energy but also new physical forms. The micromechanical tools. ChatGPT can make mistakes. Check important the matter through The explosive mass defect hypothesis proposes that the mass defect observed in nuclear fission reactions is not merely a transformation of rest mass into kinetic or electromagnetic energy, as traditionally understood, but rather a rapid and localized conversion of mass into a novel, space-filling form of matter through a microexplosive process. This reinterpretation challenges conventional thermodynamic and quantum mechanical models of fission energy release, suggesting that each fission event is accompanied by a microscale detonation-like phenomenon. A key pathway for evaluating this hypothesis is through the microscopic analysis of spent nuclear fuel, SNF, which may retain empirical signatures of such explosive processes. The explosive mass defect hypothesis proposes that the mass defect observed in nuclear fission reactions is not merely a transformation of rest mass into kinetic or electromagnetic energy, as traditionally understood, but rather a rapid and localized conversion of mass into a novel, space-filling form of matter through a microexplosive process. This reinterpretation challenges conventional thermodynamic and quantum mechanical models of fission energy release, suggesting that each fission event is accompanied by a microscale detonation-like phenomenon. A key pathway for evaluating this hypothesis is through the microscopic analysis of spent nuclear fuel, SNF, which may retain empirical signatures of such explosive processes. Theoretical basis and hypothesized structural evidence. According to this hypothesis, the energy released due to the mass defect is not dissipated solely through the recoil of fission fragments or prompt neutron and gamma emissions. Instead, it is postulated that the entire mass defect is explosively transformed into an ultra-thin, invisible form of matter, accompanied by the generation of intense pressure gradients and shock waves at the microscale. These shock waves are expected to leave behind specific structural features in the fuel matrix, such as radially symmetric voids, spherical damage zones, nanocraters, and shock-induced lattice deformations. These features are qualitatively distinct from those produced by conventional radiation damage mechanisms, such as ballistic displacement, thermal annealing, or linear momentum transfer from fission fragments. Therefore, microscopic investigation of SNF provides a critical opportunity to detect and characterize these hypothesized signatures. Analytical techniques for microscopic examination. A range of advanced microscopy and materials characterization methods are available to probe the microstructure of spent fuel elements, including scanning electron microscopy. SEM enables detailed surface imaging to detect crater-like topologies or radial fracture patterns. Transmission electron microscopy, TEM, facilitates internal microstructural analysis of dislocations, amorphous regions, and nanoscale damage zones. Atomic force microscopy, AFM, provides topographical maps at nanometer resolution, useful for identifying ultrafine voids or depressions. X-ray diffraction, XRD, allows for analysis of residual stress distributions and phase transformations that may reflect explosive pressure effects. Electron backscatter diffraction, EBSD, offers crystallographic mapping of grain boundary damage and recrystallization phenomena. These techniques, when systematically applied, can potentially reveal non-thermal, non-ballistic damage patterns consistent with the effects of rapid, localized energy release from microexplosions. Empirical indicators and preliminary observations. Previous studies of SNF microstructures, though not interpreted within the context of this hypothesis, have reported phenomena that align with its predictions. These include the presence of nanovoids and gas